Welcome to this webinar. The title is Thermolib, What's New in Release 5.2. My name is Huda Karaki. I'm part of the team that develops Thermolib. And I'm joined here by our product manager, Alexandra Lavenka, who will be helping me at the end answering some of your questions. So I'm going to go ahead and start. So we've grouped the improvements that we made in this new release into three main categories. The first of which is basically user friendliness, how we improve Thermolib so your experience with using it is better. And we've had a lot of feedback from the last release from customers about how would they like it, and we tried to include a lot of that in this new version. The next group of improvements in this new release is adding new functionalities to Thermolib. This is basically new features that were not there before. And the last part is the major improvements. This includes bug corrections, general improvements. I'll go over a quick list of these. So let's start with the first group, user friendliness. Under these, we improved the layout of hydraulic components. We enhanced usability of certain Thermolib blocks, the model setup and flow display. The components have, in general, a cleaner look, and we've added some dependency table because we've had a few users who had problems with adding new species. First of all, I'm going to go over the first three points directly in Simulink itself. So let's start with the very first one, more clear and intuitive layout of hydraulic components. I have here a screenshot of how the old Thermolib library looked like. So we are now under components, hydraulics, and as you can see, there's a redundance, for example, of the compressor block. We have here 4 kinds of compressor blocks, 2 turbines, and so on. This proved a little bit confusing because let's say you selected one compressor block and wanted to try another one, you have to completely replace the block and the model itself. So now I'm going to show you how we did this in the new version. I'll open the library. So this is the new version of the Thermolib library. Now if I go to the same directory, components, hydraulics, you can see it's been reduced and cleaned up. So now instead of 4 compressors and several turbines and so on, we only have 1 compressor. To use that, I'll open a new model. Of course, we need a setup block to be able to use the Thermolib blocks. And now I will drag the compressor into the library. By double-clicking on the compressor, now you can see that you can select the compressor type and the mask. We have here the isentropic, polytropic, mechanic. We also have a new kind, the active. This relates more to the volume flow, volume simulations of hydraulic networks. We'll get to that later. So yes, so you can now use the compressor in your model. If you realize that you want to change the type of the compressor, all you have to do is switch in the mask without having to replace the library block. This also applies to the other blocks like the pump, the turbine, and to the components under hydraulics with pressure feedback. The next point on our list is we enhance the usability of certain blocks in Thermolib. The first of which is the model setup block. So Thermolib itself uses a lot of constants to be able to run a thermodynamic simulation. And these constants were stored in a mat file that had to be loaded at the beginning of the simulation. If I go now into model setup, it was a little bit of trouble to always change the constants in the mat file and then update them here. We've enhanced this by adding here a dialog where you can directly see the values of these constants in this dialog in the model setup block. You can change them here, you can load a new file and save them as under a different file name should you wish so. Another improvement we made is if we go under things, is the flow display block. So the flow display block until now displayed the elements that are available on the flow bus in Thermolib. Some of the feedback we had is, let me first go into the mask. So before it used to show only the molar flow of the flow bus. And molar flow in most applications is not very useful, or let's say not as useful as the mass flow. And in this version now you can finally see the mass flow directly on the flow display, and you can select the common units used to measure mass flow here directly. Show this one more time. So another of the improvements that we made to the library is we gave the components a more organized and cleaner look. So beforehand we had a lot of extra ports for pressure feedback and information that we felt were cluttering a little bit the look of the blocks. These ports are now by default hidden, they're not gone. So if a user still needs to use these blocks, he can still go to the mask of each of the component, and then at the bottom of the mask you can see here I have two checkboxes: show pressure feedback port, show info port. If these are clicked, then you have the ports again, but should you not need them, you can just hide them and make your model a little bit cleaner. So now I'm going to go back to the presentation. We've covered, I feel, the first 3 points. Basically, more clear and intuitive layout of the hydraulic components. We've enhanced the usability. I've only mentioned the major changes. There's been a lot of tiny changes that I feel are too much for this presentation, and the components have a cleaner and more organized look. Now let's take a look at the last improvement. I'll switch directly to there. So basically we added a dependency table to simplify adding species. To explain that, the idea is, those of you who are familiar with Thermolib, every time you need to add a new species and a new media to the Thermolib database, you have to add it into the chemical media database. The chemical media database looks a little bit like this. I'll open the Excel file directly. So you basically add your new species in this database here up here, a new column. But so that Thermolib can use it, you have to add a long list of properties. This is represented here by the blue column. I'll just scroll down to give you an idea of how many properties for each element are required by Thermolib. This is understandably a little bit requires a lot of effort, because every time you have to search for these components, and the situation is that sometimes you don't need all of this information for certain blocks. So what we did is created a dependency table. This table basically has as components all the basic properties of Thermolib. This is here in the header of the table. To clarify this, I'm going to open the Thermolib library again. So these are the basic building blocks of the Thermolib library: the state changes and the states and properties. Mainly the states and properties. So each of these blocks has an entry in the header of this data dependency table. And on the other side of the data dependency table, you have the species properties. Here basically are the entries that represent the blue column that we just saw on the chemical media database. I'll open the table for a clearer look. So here we can see it up close. What this table basically tells us, if I need to add a new species, and I know that I only need to use the density block and let's say the molar weight blocks, then I don't need to find the NASA polynomials for this new medium. This is represented by the red cross. If I do need to find the gas properties for this new media, then I do need to enter the NASA polynomials. This is to make adding a new species easier and a little bit more clarified. So you can always refer to this table to see which properties do you really need to search for and which ones you can simply ignore. And this is now delivered with the new release of Thermolib. So now we've covered the user friendliness. We move to the new functionalities that we added in this version. We have basically here two major additions: the volume flow volume method to simulate hydraulic systems, and optimizing the tank block to solve algebraic loops in Simulink. And we have a tinier addition that is adding two new species, coal and dodecane. So let's start with the first one, the volume flow volume method. Until now, we had the pressure feedback method when we needed to simulate a closed-loop hydraulic network. Well, the pressure feedback method, just to give you a quick overview, worked by having an upstream block, which is in this case the tank, and a downstream block, and this downstream and the set of blocks in between that represent the hydraulic network. The downstream block specified what is the pressure at this point in the network. And then through several pressure feedback, hence the name pressure feedback, this was communicated back to the upstream block, which took a few iterations. Then the model ran for a certain amount of time, required a few iterations to reach the steady state and calculate the appropriate mass flow. This method had a bit of a disadvantage, is that you had this transition phase where it is not an actual physical transition in real life, but a numerical transition that was needed to calculate these iterations. And this made interpreting the results of the simulations a little bit confusing. So now we have, instead of this method, or not instead of it, let me correct myself, in addition to it is the volume flow volume method. In this method, what we have is basically, as the title indicates, two volume blocks with a flow block sandwiched in between. The flow block has the task of calculating the mass flow for the steady state. And it does that by receiving the pressure set point from the downstream volume block and communicating the calculated mass flow to the upstream volume block. This happens instantly. There is no transition time. This eliminates this numerical transition. I will show you this directly in Simulink, how this is done. I'm going to open this hydraulic simple flow model. So what we have here is a valve and a tank. The tank behaves here as the upstream block. And this is in the old method with the pressure feedback. We would define a downstream block. And inside the downstream block, we set the pressure as 3 bar. Now, when I run this model, okay, let's look at the pressure and molar flow in the network. So this is what we have. You can see here up front, there is a little bit of a transition. This is what I meant with the numerical transition. This transition would not be there in real life, and it's basically, it can lead to a confusion in interpreting the results of a simulation. So to solve this issue, we can reprogram this model as a volume in the volume flow volume method. So I'll start by noting down the pressure in the downstream block. It's 3 bar. I will delete the downstream block and remove all the pressure feedback go-tos that we have here. These are no longer necessary. Instead of the downstream block, I will need another volume block. A tank. We'll open the tank. So the tank now determines its molar output flow by setting it's equal to the input molar flow. So whatever comes, the molar flow that comes in is exactly the same on the output. The pressure inside the tank should be 3 bar as it was empty. Downstream block, that's it. We're done here. Now, the upstream tank no longer depends on pressure feedback to determine its molar flow output, but on an external input. So the block, the active block that determines the mass flow in this network is now the valve. It was programmed as passive, which means calculates pressure loss based on the key-found method, the pressure feedback. Now we select it as active. It is the one that determines the mass flow. To do that, it needs to know the output pressure. This we get from the tank. We feed it back from the tank. I'm going to need a bus selector. I'll select the pressure. This tells me what the pressure in the tank is, and I feed it back to the valve. Now the valve will tell us how much mass flow, and I'll feed back that to the original tank, to the upstream tank. That's it, and I run the model. So now, as we can see here, take a closer look, the transition is completely eliminated. There is no longer this transition. It reaches steady state directly. So now let's move on to the other new functionalities. So the next addition is using the tank block to solve algebraic loops. Until now, in the older versions, we recommended that you use the initial conditions block to solve an algebraic loop in a Thermolib model. I've highlighted this here. When you have a closed loop, Simulink needs a starting point to be able to do its calculations to solve the simulation. And this initial condition block basically behaved as a memory block inside the loop. It was possible to use the tank, but it was not optimal. And now we've adjusted the tank, so now it is the optimal choice to simulate a closed loop in a Thermolib model. And the last point in our new functionalities is we've added two new species, coal and body cane. You can find these in the model setup block at the very end. So coal is basically, we added it for power plant applications. We've modeled it as a liquid. The question begs itself, so why did we model it as a liquid? Usually in power plants, a mixture of coal and air enter the power plant, and modeling it as a liquid allows us to use filters to separate the coal and the air. And in the typical high temperature environment of the power plant, we only have two phases. Because air is obviously gas, we use gas for air and liquid for coal. And using the same method, you can also simulate the dust load using a simple gas dryer or a phase separator to separate the exhaust gas from the unburned coal. We've also added the element body cane, that is diesel used for automotive applications for engine simulations. Now we reach the last group of improvements in this new release. These are general improvements that we did. I'm going to go basically over the list of changes that we made. So first of all, we corrected species data for the following media: I-pentane, nitrogen oxide, butane and isooctane, and para and orthohydrogen. These updated species data lead to better solver stability and better conversions in the Thermolib models. We've also improved density calculations for high-pressure mixtures in the two-phase region. In the older version, it wasn't that it was incorrect, but in certain mixtures of certain species, it's quite rare cases, we had some isobaric lines intersecting in the TV diagram. This led to some problems calculating the pressure, and this is completely resolved in the new version. There is no more crossover of these lines. We've also had, in some rare cases, this did not happen very often, but simulations have led to negative density. This is no longer the case. This issue has also been completely resolved. These improvements have also led for general improvement in the iterative solver, so fewer iterations are needed to solve the Thermolib model. Finally, we've improved the capability with the new releases of Simulink, especially the 2012 A and B and the pre-release of the 2013 A. So this is a sum of all the improvements that we made. I'm going to keep the slide open in case you have any questions. Thank you for listening. I can probably show them this here. So under help, this is the installation directory of Thermolib. If you go to help, there is the PDF file of the user manual. You can also find directly in your installation directory. Where do I get the data? Yeah. Sorry to interrupt. I don't know if we've had some feedback that they cannot hear you.
Oh, okay. So maybe, can you hear better now? Probably yes. Okay, sorry then. once again, maybe so that what you see here is the links to the sources where you can find the NASA polynomials. The question was where to get the NASA coefficients to put in the Excel table. And the first source would be that you go to the Thermolib user manual. You find there links in chapter 4.5. For example, go to the NIST webbook. There's a good source for data, or the others listed here. The alternative solution is if you have measurement data available, then you can fit the data to the coefficients based on your measurement data. What you have to take care is that Thermolib works with absolute enthalpy and entropy. So that means sometimes you look at the enthalpy of water, for example, and it's quite negative. That's due to the fact that we include the enthalpy of formation and the entropy of formation. As the reference point is also mentioned in the user manual, in the former chapter, in the Thermolib background chapter, there's the reference where we consider for the elements to be 0 enthalpy and entropy, and yeah, that's the answer to that question, I hope. So that's how to find it and take care about the absolute enthalpy, especially if you want to involve the species into chemical reactions. If you don't intend to do chemical reactions with the species you insert, then in principle you can choose your reference point arbitrary. So that means you don't have to take care about enthalpy of formation and entropy of formation. So then you are more or less free, except maybe the interpretation of the enthalpy balances around. Then if you have multiple streams, for example, in a heat exchange or something like that, then you have to take care of it a bit. Yeah. There was another question about coal, especially. Maybe I can take over presenter role because I have opened the corresponding chapter in the user manual already. What you see here is an extract from the user manual. You should see now my screen. And there on page 21 in the Thermolib user manual, you find here the reference point for enthalpy and entropy. So what I just talked about, that at this reference temperature of 298 Kelvin, we consider the enthalpy of the ideal gas to be the enthalpy of formation. So that is the reference point. So maybe that answers the question. So that means the enthalpy of combustion of coal is a result of this absolute enthalpy, because it's including already the chemical portion and the latent heat, or the sensible heat. And so as soon as you involve any species in a chemical reaction, the enthalpy balance of the chemical reactor will be input enthalpy is equal to output enthalpy. The question is only what will be the output temperatures and what corresponding to the different concentrations. So that means the enthalpy of combustion is inherently included in this formulation. So you don't have to take care of explicitly giving any enthalpy of combustion of any fuel, be it dodecane, coal, methane, whatever. That's already done by the basic thermodynamics by using the absolute enthalpy, including the chemical energy as well. Yes, one more question. Is the TH get chemical media data still the same in the new version? So yes, it is. That means this tool is still available, so you just can put TH get chemical media data on your command line, and it will pop up a dialog where you can import the chemical media data Excel file into the MAT file, which is then used finally by the simulations. So that tool is still available. I hope that answers the question. Yeah, we can close for today.
Yeah, so thank you very much for listening. This webinar will be up on our YouTube site very soon. And please send us an email, drop us an email if you have any further questions or inquiries. Thank you.